Everybody, welcome. Welcome to the Institution of Mechanical Engineers Railway Division South East Centre talk. It's great to see you all here today. My name is Toby Johnson. I'm the chair of the South Eastern Centre of the IMechE Railway Division, and thank you for joining us. Tonight's event will be recorded, so if you can mute your microphones and turn your cameras off, that would be great, and we'll have a question and answer session at the end. So tonight I'm very excited to welcome our guest speaker, Professor Nick Tyler. He's going to be giving his talk on the UCL PEARL facility. As I said, Nick has agreed to take questions and answers at the end, so please put those in the chat as we go through, or raise your hand and we'll take questions at the end. Just a quick notice from us at the centre. Our next event is Rolling Stock and the Road to Delivery. That's on the 20th of April 2023, and as you can see, I didn't put the speaker's name in that slide. But that will be a hybrid event at RSSB's office and also on Teams, and it will be preceded by an AGM. So I look forward to seeing you on the 20th of April. So without further ado, I want to introduce Nick. So Nick Tyler is the director of UCL Centre for Transport Studies and the Chadwick Professor of Civil Engineering. And he investigates the ways in which people interact with their immediate environments. And Nick set up the accessibility group within the Centre for Transport Studies, which has a total research portfolio of more than £40 million for projects directed towards making the world more sympathetic to people's needs and creating a sustainable future for both people and the planet. His work is highly transdisciplinary, and his team includes and works with engineers, psychologists, architects, musicians, economists, to name just a few. He's also co-founder of the UCL Universal Composition Laboratory, which undertakes multisensorial spatio-temporal design. That's a bit of a mouthful for me to say, but it sounds very exciting. And he's a fellow of the Institution of Civil Engineers and a fellow of the Chartered Institute of Highways and Transportation, also a fellow of the Royal Society of Arts. And he's also appointed a CBE in New Year's Honours 2011 for services to technology, and elected a fellow of the Royal Academy of Engineering. So I can't think of anyone better to give tonight's talk. So without further ado, over to you, Nick.
Okay, well, thanks very much and good evening, everybody. I'm just going to attempt to defeat my experience with Teams and share a screen. And let's see what happens. There we go. It's telling me to update my driver. Right, let's see if I can find. It's not letting me do this. Hang a minute. I'm having trouble here. Let me just try again. Don't want to update the driver. Windows 15 should be, there we go. What's it doing to me? I always love this technology. It's right, I can find it here. So why is it not uploading it? It is just going invisible on me. This is annoying. Just disappears.
Perhaps you could email me can you email me the presentation and I can share it?
Yeah, let's do it that way, because yeah.
Do the next slide, please.
Yeah, yeah, sure, yeah. There we go, Toby.
I'll share it.
Yep. Okay. There we go. God. It's now saying, hang on, I have to do this via WeTransfer. Hang on. I'm sorry about this. This is one of those Teams things. Oh, come on. Right. Okay, what a joy this is. For some reason it's crawling around. Here we go. There we go. Right. Getting there, getting there, getting there. It says it is going slowly, by the looks of it. So while that is happening, I guess we can I can start to sort of talk a little bit about the facility. So what I'll be talking about is a facility called PEARL, and PEARL is stands for the Person Environment Activity Research Laboratory. And what that does is essentially it kind of does what it says on the tin in a way. We study how people do things in an environment, and that means that we have to build environments for them to do it in and be able to do that at a scale that people find it credible. So that this is kind of a different sort of laboratory from many that you might be familiar with, which is that most laboratories you try and make the world small and you study it within the laboratory, and this laboratory is one where we kind of make the world person size. So we build in here, we build, or later this year, for example, Network Rail is coming to build a station here. We built urban parks in here and supermarkets and things like that, and it's been a very, very interesting case of how you design a building that can actually represent the world that we want to build in enough detail that we can try and make it really work for people, so that we can understand, we can study them, we can instrument them and see how they actually respond to things. So inside that laboratory, the space that we have there, we have about 44,000 cubic meters of space. And in there we can build things like stations, but we can also build outer space we've been asked to do, things like that. So we can make the space into whatever we want. So if you imagine kind of almost like a film studio in a way. If you imagine something a bit like a film studio, that's the kind of thing that we're talking about there. Toby, it says that it has sent it to you, so it should be arriving at some point or other on WeTransfer.
Yeah, I've got my emails open. I've not received anything yet,
Okay.
but I'm refreshing it. So as soon as it does, I'll share. Unless you want to try again quickly.
No, it's fine. It's fine. I won't risk it. So it obviously was being very upset with me today. So the point about Pearl is that we have this kind of idea of making the world a better place. And to do that, what our sort of idea is that to do that, we want to understand better how people interact with it so that that interaction can be then incorporated into the design. And that applies to infrastructure, applies to vehicles, and so on. So in our thinking around that, one of the things that we've done is to kind of almost take the algorithm out of the kind of engineering design that happens sometimes. So for example, I mean, a good example of this is the aircraft that crashed onto the Hudson River, for example. How long ago was that? 10 years ago? So when the pilot was coming down, he realized he had to crash that aircraft onto the river at a pitch of about of exactly 11 degrees. Because if it was at 12 degrees, then the back of the plane would hit the water tube first and it would spin and overturn backwards. And if it was at 10 degrees, it would hit the engine cowlings would hit the river first, and then it would flip over forwards. So he had a very, very precise piece of flying to do with no power, no instrumentation, and only very manual kind of go at the controls. And he at one point he said to the co-pilot, "Well, you do the code, you do the checklist," which of course they have to do. He said, "I will fly the plane." And how he actually brought that plane down was essentially through feeling through the steering column, through his body, through his eyes, his ears, all of those things that enabled him to be able to control that aircraft and bring it down successfully onto the river in such a way that and in the end, of course, nobody was killed in that process. In the meantime, the co-pilot had only got about a third of the way through the checklist, and to me, this is a kind of the significance of this is that the checklist was kind of an algorithm. Somebody invented the checklist to say, here we are, we've got this aircraft, lost power to both its engines. What you need to do is this, and then you do that, and then you do something else, and you work your way through this exercise, and then you get to the end, and you've checked out everything that you need to do. The problem was that the assumption behind that algorithm was that the engines would fail at 10,000 meters. And of course, their engines failed at something like 1,000 meters. And so they had a real problem with that. He only got a third of the way through the checklist by the time they hit the water. And what that meant was that the air valves were actually still open when it was sitting in the water. And the aircraft was actually slowly sinking as people were standing on the wings ready to be rescued. Now, the key for me on this is that what that is talking about is the difference between how humans do things, how human beings work their data, the data that they receive, and what they actually do, compared with how, for example, a computer does things. And we have a sort of tendency to think that the brain's a bit of a computer, and we tend to sort of try and order things in that kind of way. But actually, humans are much, much better at very multidisciplinary, very multisensorial kinds of decision-making processes. And that's kind of what we do really well. And what we're trying to understand in Pearl is how we can actually understand those processes and incorporate those into the kind of design of mobility and transport systems like railways. And one of the things that we find we have to do with that is to think about things in a much more flowing kind of way rather than statics. So rather than sort of try and chop up our perception of the world into pieces and then say, I understand this piece, and then we have that piece, and then we have another piece. This is actually thinking very much more about the flow, how things actually move through, and the concept, for example, that you can't jump into the same river twice, because both the river is different and you are different, and that sort of thing. And that becomes actually really important, even when we're doing very routine things. So how we consider, for example, the idea of mobility when people moving around, which of course is something which the railways help us to do. But what are we actually trying to do with those sort of mobility systems? And one of the issues that we have there is how we actually conceive mobility. And I like to think of it as in four pieces. The first one is, yes, there's movement. We do move, but it's different from mobility. So movement for me is the physical displacement of things. I move a train from A to B, that kind of thing. We have a concept called the local deficit. The local deficit is the fact that where I am doesn't have everything that I need or want to, or where I want to be. So therefore, there's a lack. And in a sense, mobility makes up for that lack by enabling me to get to wherever it is that those things are. But that only works if everything is accessible. So we need to have, in the mobility concept, we need to have accessibility, so it is open to all. And we also have transport. And so for me, when I talk about transport, it's as the means by which those things happen, in particular, the sort of kind of means of other things happening. And then we can go, we can then move that. So it's kind of the means of enabling movement, if you like, is how I see transport. So Toby, thanks. You got your slides. So if you can move on, I've gone through about 11 slides. So you can. Yeah, and the next one.
Stop.
Yep, yeah, keep going. Next one. That's it. Thank you. So what we talk about in transport a lot is about, so people obviously moving, so what's the trip purpose? And there's a lot of sort of sociological research and behavioral research in how people move on, why they're actually traveling, and that trip purpose thing. And we tend to box it into really, really simple things, like they're going to work, or they're going to leisure, or they're going to education, and things like that. So really, really simplistic things. And if you go to the next slide, please. The whole issue that we end up with is that we design our mass transit systems on the basis of that aggregate assessment of those multiple trip purposes, but it is incredibly simplistic. And if you take a train, so if we go to the next slide, if you take a train, this is a actually I took this off a stamp. So in 1909, this was an advertisement for the District line in London, and you can see this is the peak hour, and it's saying commute from the suburbs. And there they all are, commuting from the suburbs, and they're all sitting very nicely in the train, reading their papers. We have a nice mixed gender train there. It all looks very good. Top hats, all very fine. If you go to the next, please, Toby. Yes, this is more like the reality that we have, where this is I think this is the Victoria line, but this is a case where we have people in London around about 4.5 people per square meter in the peak on average, and that is what you kind of get. Now, that image of the present is very, very different from the image of something over 100 years ago as to what it actually meant to commute from the suburbs. And one of the reasons for that is I think we have not really grasped why we have mobility and why we do it, and therefore when should we do it. And I'm going to talk a little bit about that later on. If we go to the next slide, that is actually in Japan, in Tokyo. And in Tokyo, they regularly run their peak trains at around about 7 people per square meter. And you can see the kind of anguish of the people standing there on the train, waiting for the doors to close, so that the train can actually move. But the density in there, if you look at those people, they are almost contorting themselves not to be looking at each other. So, and one of the reasons for that is that when people are within around about 40 centimeters of each other, that is either a space into which you let people, because they are friends or family or something like that, people that you know well, or it is an aggressive act to enter that space. And therefore, in that train, there are people, and actually also in the London case, what we actually have is people being put into a situation where the body's natural response is that this is an act of aggression. And what happens, if you go to the next one, Toby, what happens with that act of aggression is that your brain stimulates the release of cortisol, for example, as a response to that, in order to cope, in order to prepare you to survive, because that's the brain's one job. And those stress effects come on incredibly quickly, because it's a very protective thing. It's how you are sort of hyped up to be able to react to that stress in a good way. Do you run away? Do you fight? Do you chase something away, or whatever it is? But they carry on reacting. It doesn't switch off very quickly. So it goes on for certainly minutes and often hours. Typically would be hours, 2, 3, 4 hours, sometimes over days. And for some people, it never quite resolves. So that is interesting, because that commute is imposing on people the stimulus that creates that stress response that goes on for hours, that therefore affects everything that you do during that time. And we're doing that kind of twice a day. And the impacts of that are that it is affecting people a great deal. Now, normally we set that aside. We're kind of used to it. We have to go to work, and that's kind of part of the trog of going to work. But actually, it is a health problem, and for some members of the population, it is a severe and chronic health problem. And we really need to be sort of thinking about how do we try and resolve this problem? Why are we inflicting all that stress on people? So if we go to the next one, so one thing we might be able to do is to think about how we design the trains. And so what we've tended to do is we've tended to reduce the seating space take by seating. If you remember, that district light train, funnily enough, also had seating along the sides, the linear longitudinal seating on the train, and increase the amount of space for standing. And what that does, in theory, is to reduce the density of people standing in the trains. You've got more space, you can put more people in it. But actually, what happens is you're simply increasing that exposure. And we can see this when we start to examine how people respond to that kind of pressure. So if we go to the next one, Toby. So one way of doing this that we found, we did some work for London Underground a few years ago on the new train for London, and as part of that, we ran some experiments just give ourselves baselines and things like that, where we took an empty train carriage and simply filled it up with people. And if you go to the next one, what you have there is, if you like, this is the graph. So the solid line on that graph is showing you the boarding, effectively the boarding rate, people per. In that particular case, I think it's per every 2.5 seconds or something like that. And the dotted line that you see there is the cumulative boarding number of people boarding. Now, at point 1, what you're seeing there is when the doors open and the people first flood into the train, there's nobody in the train, they all go very quickly, so the boarding rate is very, very high. But after quite a short time, that drops. And what's happened there is that the people have actually basically filled the seats. And the next people to board after the seats have been filled are then saying, where do I go? I don't want to be in this space. I need to go somewhere. So the boarding rate, that reflects at the rate at the door of people being able to board, because essentially people have got on the train and they've kind of stopped. And then they realize they can actually just go into the most convenient space for them is opposite the door that was open. So they go in there, and you see when they do that, the boarding rate increases a little bit. And then there's only a limited capacity for that. And then the boarding rate falls, and you go into this long decline of boarding rate until eventually the very last person gets on 55 seconds after the door opens. So that train was there for a minute to load all those people into it. And that's the kind of thing that's going on. Now, they are reflecting passenger densities. So when you start to see the first drop is when the passenger density is over 2 people per square meter. And you'll find that when that density eventually goes down, as the density goes up, the boarding rate goes down. And in this case, it got up to about 4.5 people per square meter until the very end when it was around about 6. Now, if you go to the next one, if you take that to an extreme, and this is a photograph of in Tokyo a few years ago when they had what they call oshio. These are the people who push people into the train, and you can see, you can imagine how solid that train is with people. This is getting on to well over 7 people per square meter, and probably 8 or 9. Simply to do that. This is an amazingly inefficient way of running a railway. Actually, the amount of time it took to get the train out of the station was absolutely massive. So not only was it very uncomfortable for the passengers, it was actually awful for the service as well. So when we looked at for London Underground, go to the next one. When we looked at London Underground, the new train, we were asked to have a look at that. And what you see here is the idea from London Underground that the doors, measuring out the doors, having the doors the same distance apart all the way along the train. And one of the things that we saw was that at that distance, it was a very specific distance, and at that distance, people would move to the other door if they saw that door filling more quickly. So that, well, sorry, the queue moving more quickly. And that is actually very useful because what it does is it means it evens out the dwell time for each door, if you like, along the train. So actually you get a much more efficient and even boarding. You're not holding the train waiting for one door to sort itself out. It tends to be even itself out. If you go to the next one, in this case, what we were doing in there was, this is a case where we were boarding people on and off the train, and seeing how they were doing. White hats were getting off, red hats were getting on. And you can sort of you can almost see a pattern there. If we go to the next one, you'll see that one of the things that happened, one of the things we were looking at, for example, is what should the seat look like next to the door. In this case, it was tip-up seats. And what we found with tip-up seats was that the people getting on tended to get on at the sides of the door, and the people getting off walked out of the middle of the door. Or maybe I should have reversed that. The people going off go through the middle of the door, and the people getting on get on at the side of the door. And why I reverse that is because that's probably the sequence that it happens. So it's the people in the middle that are directing that. If we look at the next slide, in this case, the people getting off are going out by the side of the door, and the people getting on get on in the middle. And this is because we have perch seats. And that is a difference. Now, when you think about the efficiency of the platform and the train interface, actually, it would seem that tip-up seats might just be a little bit better than perch seats in some cases, because you would be lining up your passengers on the platform by the edges of the door, which is more convenient, and the people getting off go out through the middle, and the people getting on can get on the side. In actual fact, in the overall thing, it makes very little difference to the dwell time of the train. But if you actually have the door, if your door open time is sort of less than maybe 20 seconds, 30 seconds, something of that order, then it's actually better to have tip-up seats than perch seats. So it depends a little bit on what you're expecting to happen, but you can see in that image what that crowding begins to look like. So if we go to the next one, this is also in Japan. This is where one of their responses to this is actually a sort of kind of cultural thing almost, where there is a queue. And they actually mark out spaces on the platform for queues, and people will queue on the train, and the queue just goes. And when the train is full, the queue stops. But they do try to get as many people on the train, and they do still have very high densities. They don't use Oshiya anymore, but they do have very, very high densities on the train, and people kind of accept it. When I ask them why do they do this, they just say, well, I have to go to work. And that's a fairly common response. On the other hand, if we look at the next one, which is also in Japan, this is the Shibuya station in Tokyo. This is the crossing outside it. That crossing has 45,000 pedestrians an hour crossing that road, and they never collide. They can do all of that maneuvering, and that's because it's a relatively free space, even with massive numbers of people. They can actually move and move around and avoid each other, but you still have huge density, but it's moving, it's going in opposite directions, and they are not colliding with each other because, in a sense, the space is less constricted than it obviously will be on a train. So what do we do about all this? Well, this is where Pearl comes in. So go to the next one. And actually you can go to the next one because I said that. So what we start off with is that, okay, so all these interactions, people, whether they're dense or whatever they're doing, their interactions involve the brain. It's basically all driven by the brain. And if you go to the next one, the brain basically is there to survive. So the brain works in a kind of predictive model. So if you go to the next one, this is a kind of schematic of a reaction. So if we start at the top, start with the environment, basically you get your stimuli in from the environment. The brain is sitting in a black box. It doesn't see anything, doesn't hear anything. It just gets electrical signals. So it sits in that black box. It gets fed data from the environment through the sensory pathways. Those sensory pathways are then processed, and that induces a response from the brain. So the cortisol that I talked about, the cortisol stimulus that I talked about before, is a response that the brain has made to the sensorial information that it's had. That then drives the perception that the person has of the world around them. That then causes them to react. So they then do something. They move, or don't move, or they jump, or they run, or whatever it is that they do. That then changes the environment and goes on. So if you go to the next one, we can then look at that as a kind of picture of perception where we start off with our initial perception of the world, kind of, I believe the world is like this. I then learn a bit more about that world through all that data, through all the sensory information. I then trust I've got a better picture of the world. My brain is going to respond to that, and then I get my reactions. I do things. And so if we go on to the next slide, that then turns into work which was done about 10 years ago in neuroscience, where they started thinking of the brain as being very much a predictive organ, and that it is, before they thought it just simply responded to the world. Now they think it actually predicts the world. And it's kind of saying, actually, in this state, with this sensory information, the last time that happened, this is what I needed to do. Therefore, I must release some adrenaline into the system so you can run away faster or something like that. So you have that in Bayesian terms, you have a kind of prior probability of something, which is your initial perception, if you like. You then get your evidence in, your sensory data. You then have your response. You then have your, which is your hormone release, for example. That then induces the posterior probability of your perception given that evidence, and then you react. And that goes on all the time. And that's kind of how the brain is working. So if we go to the next one, and what you do with this one is you start at the bottom, and essentially you go in this sort of cycle of the environment tells me something, the senses relay that to the brain, I respond, I have a perception, I react, I change the environment, I sense, and so on, and it goes on and on. And you've been doing that since before you were born. So the next one, please. So what Pearl is kind of a way of trying to understand that by kind of representing it and giving the opportunity for us to be able to put people into the space, a little bit like being in a neuron in the brain. And so the next slide, please. The next one is, so how actually do we do that? So the next slide is a kind of very simplistic picture of it. So what we say is that understanding that mobility that I was talking about earlier is really about how people make decisions. That collective movement that we were talking about is all based on individual decisions. So we need to understand how individuals do this, those reactions of individuals. Those individual decisions are based on their perceptions of the world. The perception is driven by the predictive coding model, the Bayesian model, the responses and things. The predictive coding is then in turn driven by, or based on, the combination of the lived experience that people have and the sensorial data, and putting that all together to be able to do that. And how we therefore do that in Pearl is to have controlled experiments where we can actually go through that sequence. So that's the thing. So the next question is basically, to put that into a nutshell, all we know about the environment arrives via our senses. We process that to create a perception of that environment. We act on the basis of that perception, and then the environment adapts. So if we go to the next one, how we build that into the laboratory is that we take this idea of the pathway from the environment to the neuron and back drives the design of the environment. So when we were looking at this design of the new metro, for example, what we're looking at is how the people interact with each other while they're getting on and off, as well as how they interact with the train. So the passenger train interface isn't just simply the hardware of the train and the platform, it's actually the people crossing that actually gives us that environment. And the next one. So we create those environments. So Pearl, this is a picture of a bit of it. We have lighting where we can simulate anywhere on the planet at any time of day. That's unique. We've had people in from Hollywood wanting to calibrate their cameras in here because nowhere else they can find can actually give them the color sensitivity of the human eye. The physical touch light, we build and simulate life-size environments. We can induce smell in there. Last week we had some experiments on smell in street environments. We can simulate soundscapes and acoustic environments, so we can make it sound like a small bedroom, or we can make it sound like St. Paul's Cathedral. We can run trains through there, aircraft through there acoustically. A few weeks ago, we had Oxford Street and Tottenham Court Road Junction outside the Elizabeth Line station, acoustically represented in 3 dimensions so that we could actually test some interventions being done on electric scooters. I'll talk about that a little bit later. And we can do all of that at the same time. The next one. To make that controllable, the first thing you notice is that its decor is very black. And that's because we can then take the world away, and then whatever you actually see is what we want you to see. And that's actually really important. So all of the lighting is set above the line of the vertical peripheral field. The horizontal peripheral field, we don't put straight lines in there because as soon as your visual cortex spots straight lines, it knows it's not natural. So we make sure that the walls are slightly wavy. That means that we can set the width and the length beyond your perceptual range. And what that means is that we can convince you that the world is bigger than it actually is. So the building looks bigger on the inside than it is on the outside. The background sound is very low. It's what a planner would prescribe for a bedroom. And the reverberation time is very short, it's about 1 second. So, and that we do that so that we can alter the acoustics. We can create longer reverberation times. What you can't do with a building is reduce them, except without massive difficulty. Next one. So what do we do there? Well, we create environments. So this was a case, we did some work for psychiatry where they were interested in autistic children in an urban park. So we created an urban park. We had back projected images around a space. You can see them there on the right. But we also had real plants and things in there which we could treat with light from our lighting. So they were all terribly happy and grew amazingly rapidly and very, very happy. They got very depressed when they went back outside, so that we could do experiments on autistic children playing in a park where we were being able to introduce the urban noises, which they see as a conflict between the calming effect of the path and the maybe more aggressive way of the urban noise, the traffics, the emergency vehicle sirens, the helicopters and all that sort of stuff. So we can see what is actually causing them the most stress. Next one. And then we built a supermarket. We built this one for Oxford University. This is a supermarket. The first site just looks like a supermarket. At second site, it looks a slightly strange supermarket if you look at all those packets of eggs. This is a supermarket designed to look like a supermarket does to somebody who is autistic. So they have very difficult chance choosing which packet to choose from a shelf, for example. And we did this for Oxford University to demonstrate the end of a research project that they did to supermarket owners, to show them just how alien their supermarkets appeared to people who are autistic. So the light was much brighter and sort of harsher. The sound was loud and harsh. The smells were quite brutal. The intensity on the shelves was very great. And then we could show them what that supermarket would look like when it was not being set up like a supermarket for, or how it appears for autistic people. And so they could actually realize that there are things that they could do which would be fairly cheap, but which would actually make the world a lot better for not just for autistic people, but actually for quite a lot of the rest of the population as well. The next one. We did some work for Transport for London on bus legibility, and so you can see the bus in there. What we were doing is they're looking at different technology for their destination blinds. And so we were testing that. So how easy is it to read from different distances for the different technologies? What happens under different lighting conditions? And one of the conditions that we put in there was fog. So we introduced fog into the space because it disperses the light in a slightly different way. And how much does that affect people's ability to read the different technologies, trying to demonstrate the same sort of signage? And then if you go to the next one, we can then put smoke in there, and then we combine the smoke with the light, and you can then create kind of dense visibility down to about 60 centimeters visibility. And we can then combine that kind of capability with sound and light and smell, of course, to create simulations of environments, for example, explosions and things like that. If we go to the next one. So that was all about the environment that we create. So what do we do with the people? Well, we instrument the people quite a lot. So this person has eye tracking cameras, accelerometers, markers for a 3D positional camera. We also put brain scanners on people. We have all sorts of physiological measures that we take and things like that, so that we can actually measure how the body is responding, so that we can begin to come back to that piece around how is the human brain dealing with these environments, so that we can understand how the environments work better. So if we go to the next one, I can give you a little bit of an example of the sort of things we do, which is we were asked to produce a sound for e-scooters. A lot of people very panicked by e-scooters, and so the scooter rental companies want to operate in London. Transport for London said, you have to have a sound if you want a license, and they came to us to ask us to create a sound for them. So if we go to the next one, and what we're looking at here is an alert sound, and the alert sound is essentially something which had to give you the sense that there's something coming, so that when the scooter actually appears in your visual field, you're not shocked. So the next one, please, Toby. So how we did this, we had like 3 phases of experiment. So on the left, you see the initial one where we just put about 150 different sounds, and you can see there 2 kind of semicircles of loudspeakers. And the table in the middle, we sat the participants there facing away from the loudspeakers, and we just played about 150 sounds to them randomly from those different speakers, and they had to tell us where the sound was coming from. And some sounds had failed absolutely miserably. Some sounds were quite successful. So out of those 150 sounds, we saved 14 that we took onto the second stage, where we simulated the movement of the sounds. So now the sounds were dynamic, and you might just be able to see in there the arrangement of speakers to create a little small ambisonic zone. So they were basked in Oxford Street and Tottenham Court Road, as I mentioned earlier, and the sounds would be moving along those speakers that you can see lined up to that, so that they would tell us whether it was coming from the left or right, and how quickly it was moving, and when they could detect it, and so on. Out of the 14 sounds put there, we retrieved 5 that worked, that we then used in the third phase. So in the third phase, we expanded that ambisonic zone, so it was then about 8 meters in diameter. And then we could put the sounds onto the scooter with small speakers, the kind of speakers that would end up on the scooters. And then we run the scooters at different speeds, different positions relative to the participants. And they had to tell us when they detected it, but they also had to tell us how shocked they were when it appeared. But in addition, we put brain scanners on them, so that we put an EEG. So if we go to the next slide. So what happened with this? Thank you. So what this is these are 2 printouts of of a person listening to this. This is their brain scanning. So that sort of colourful circle at the top is a neuroscientist's image of a head. And the bottom of that circle is, if you like, the back of the head, and the top is the front. And what you're looking at there, the red part of that is where you have the most radiation coming from. From that, it's electromagnetic radiation coming from the neurons firing. And you can see the red is at the back kind of left-hand side, and that is the visual cortex. So the scooter has appeared in the visual cortex, and about 372 milliseconds, it tells me, after the scooter appeared in the peripheral vision, there is a spike in the neuronal activity in the visual cortex. That is absolutely what we would expect to see. And you see that spike, it's around about getting on for 600 microvolts. If you look at the lower graph, same thing with the head. And what happens in the lower graph is kind of the same thing. You get a spike. This time it's a little bit earlier. We don't know if the 20 millisecond difference is significant or not. It's slightly earlier. And more importantly, it's much, much lower. It's around about 100 microvolts. Now, what that is that the one at the top is the output when we sent a scooter through with no sound on it, and the lower one is when we put a sound on it. So what you're seeing there is that the brain is responding very, very strongly to the surprise of seeing the scooter in the peripheral vision. And the bottom, when it's got a sound, the brain is responding, but it's not responding anything like as strongly. And that's kind of what we were looking for, because we didn't want it to be such a shocking sound that you are shocked by the whole thing and you're terribly scared and you want to stop and do things. So we didn't want to increase the shock by having the sound. What we wanted to do is to reduce the shock a bit so that it became something that you could associate more tranquilly. And when we asked people to rate their surprise level on a score of 1 to 5, on the top one with no sound, they were scoring generally the surprise of seeing the scooter appear was around about, on average across all the participants, was around about 4.5 out of 5, so pretty high. And in the lower case, when there was a sound on the scooter, we had they were responding, their response was around about 1.7. So much, much lower. So what we're looking at doing, that is now going out to trial on street. And what we're sort of looking there is to see how we can actually manipulate, in this case, the sound of the scooter to deliver, if you like, the human's natural response to a sound, and not something very shocking like an emergency vehicle siren or something like that, but to try and get that much, much more tamed down so that we could actually enable people to feel more comfortable with e-scooters around, because they're going to be here whether we like it or not. They're here, but they're not going to be shocked by that. So, and that's a very, very short summary of a much more complex project, but to give you a rough idea of the kind of level of detail that we go to in order to be able to understand how we build a better environment. So if we go to the next one, what we're really trying to do then as part of this, and where I think this comes across for you, is we're trying to figure out how can we design a rail system that actually meets the needs of the human brain. In other words, the bit before you're consciously aware, those brain scans, the person at 372 milliseconds after the scooter appeared, the person was unaware. It takes about 500 milliseconds to enter your conscious awareness. And so what we're looking at is, can we actually work out how to design something like a railway system for the pre-conscious brain, because that is what drives the response that the body is going to make, the person is going to make, and therefore how well they feel they are in the world as we have it. So that's my quick romp through Pearl. I really apologize for the mess up at the beginning on the technology. If you take the next one, then you've got where you can find us. So thank you very much for the opportunity to describe a little bit of Pearl. I'm very happy to take your questions.
Thank you very much, Nick. That was a fantastic presentation. Really, really interesting. I thought it was. Thank you very much for taking us through some of the the science behind some of those fantastic experiments that you're doing, and bringing them to life with some excellent examples. Graham, do you want to ask your question?
Yeah, hi Nick. Very, very good presentation. It's very fascinating actually, and that's where my question came from really. Or was there anything that really surprised you, such that you sort of stood back in amazement when you first started doing those sort of tests? I mean, is there sort of a big wow moment on something that you didn't expect and it came out of the blue?
Well, actually, I can think of a couple that are very, very different. So one was when we were doing the new train stuff for London Underground, the significance of getting the dwell time under control. So the variation, we ran this for the Victoria line, and if we can reduce the dwell time in each station by between 1 and 2 seconds, about 1.3 seconds. If we reduce it by that much, you could save a train off the fleet.
Yeah.
And or you could, if your signaling system were to permit it, you could run a higher frequency. But it comes from getting the train out of the station. And that's why I think that thing about the doors being the same distance apart all the way along the train is so important, and why psychologically having them at 5.5 meters apart works. If it's 6.5 meters apart, people wouldn't transfer, and at 4.5 meters apart your train will fall apart. So 5.5 meters is kind of a sort of a working place to do it, and keeping that consistent along the train. I think we'll see real benefits in there in able to keep the dwell time consistent in the service. So that was one. The other was, I think, the e-scooter one, the one that I showed there. I think that really was a wow, because we kind of predicted that something like that would happen, but actually to see it was really nice. I think that was a real wow moment, and that kind of showed me that yes, we are on the right track here of trying to do this, and we do have technologies that can actually help us to do that. So yeah, I think those would be two, but there have been many, but those would be two.
Oh, thank you, Nick.
I was just having a look in the chat. There was one question, is whether you can play us the sound. That was the shortlisted one.
I don't even attempt it on this, given my technological problems. Basically, the sound, if I were to describe the sound, if you imagine it, I mean, it doesn't, of course, it doesn't sound exactly like this, but if you were in a very boring meeting and you wanted to attract the attention of somebody, you just sort of go something like, right? So that sound, which you might write PSST or something like that, so that has all the characteristics. So you have a very hard start. You have what we call an onset. You have a broadband kind of body of the sound. So the sound is there's quite a lot of frequencies in there. It's relatively high, quite a lot of frequencies in there. And the end of it is quite sharp too. So on the end of it, the T on the end of it. Now, the real trick with this was to realize that when you say pst, when you make the letter P, you close your lips, you increase the air pressure, you part your lips, and what the first thing that happens, you get a non-vocalized air. And from some other work we were doing on synchronization and location and things like that, I realized that there's a benefit to a 2 millisecond gap. And so we put a 2 millisecond gap between the opening of the onset of the sound and the body of the sound. And as soon as we did that, people could locate the sound.
Wow.
When you can have the same sound, you just join them together and it doesn't work. Put the 2 millisecond gap in and it works. And it means that we can then make the sound less loud, because what it's doing is it's working with your hearing system and how your hearing system interacts with your eyes and all that sort of stuff. And that enables us to be able to have a sound which is actually about the same level as the background traffic noise, but you can hear it. So it's that we're trying not to increase the urban noise. We have plenty of that already, so we don't need to increase it. Yeah.
Yeah, not shouting over everything else that's going on.
So,
yeah. I mean, as you were presenting that, made me think whether the rail industry can learn anything from it in terms of helping track worker safety, in terms of
I have wondered about that.
the audibility of train horns and whistles.
Yeah, I have wondered about that, and I think that would be something that would be really interesting to look at, because it's clearly a massive problem. And I think what we've kind of learned from this, I'm not saying this is the answer to everything, of course, but what we kind of learned from this is that the human ear is actually really sensitive to quiet sounds, to quite low level sounds that have certain characteristics. And that's because the way we evolved. So genetically, we are kind of at the savannah. And in the savannah, there isn't very much. The background noise in the savannah is about 20 decibels, and there's kind of nothing. But you would hear the snap of a twig.
Right.
And that snap of a twig might be a lion coming to eat you, or it might be a monkey that you could go and eat. So we are all here because an ancestor of ours made that call.
Yeah.
So we are not very good at loud noises. So nightclubs, for example, have induced a massive shift in the early onset hearing loss into the sort of 30s from the 50s and 60s. And that's because they are subjecting themselves to massive amounts of noise. Now, your train horn, like your emergency vehicles, is very loud, and I'm not saying it shouldn't be loud, but don't get me wrong. But I do wonder whether we should be looking at the kind of shaping of the sound a bit more, and whether that is something that we could actually go a similar kind of thinking as to the one that we used with the e-scooter. Obviously, there's a different circumstance. You're not trying to talk to somebody from 2 meters away. You're trying to talk to them from much, much further away. But actually to start to think about that a little bit more, and maybe there are characteristics that could be added into a horn sound that could actually work and enable people to be better protected in the end. I think that'd be a really interesting idea.
I think so. Yeah. Graham, do you want to follow up on that?
Yeah, that's a very interesting discussion about the train horns, because there's a very vast difference between the type of horn used on mainline trains and the type used on the underground. And those of us on the underground sort of know and love our 3-tone whistle, but it is a 3-tone whistle.
Yeah.
And not being an expert in this, it sort of made me wonder whether 3 tones has any particular benefit over a horn, which probably goes through quite a wide frequency range in its when you press the buttons for a horn to go. So maybe that's an answer we should be asking ourselves. Yeah. Well, at the same time, we're getting complaints from people because we're blowing the horns to test them in our depots. So we were at one point looking at what we called a silent whistle test. We never really got very far with the development of it, but it was still a useful thing to think about. Yeah, very interesting. Yeah, I've just been having a conversation this afternoon about testing sounds of electric vehicles and how would you do that? And it's not a dissimilar comment, but no, the 3-tone horn kind of makes sense. The 3-tone whistle rather kind of makes sense because you've got relatively high. It's important to have a fairly broadband frequency because people's hearing does cover about 20,000 kilohertz, so 20,000 hertz, and you want to cover as much of that as you can, because some people lose hearing at the top, some people lose hearing at the bottom, and so on. So you want to, so the 3-tone whistle is good for that because you're covering quite a wide range. I think also the way it starts is quite important. And one of the things we learned from the scooters was the start of the sound is really important. The mainline train horn I see as kind of a bit Neanderthal. It's loud. To me it's a bit too low, and I think it has no definition about starting it. So I think there's things that'd be really interesting to test that out. Maybe I should get hold of your 3-tone whistle and have a go at it. That'd be rather fun. You'll have trouble getting one because they're like gold dust. Yeah. Very sought after. Oh, well, maybe we can disturb a few residents, come and record it. Yeah, we could start with that. Sounds like a good idea. Thank you, Nick. Okay.
There's a question that was in the chat, which was, can this approach or these techniques be used on a bigger scale? There are a lot of stations that are in a dilapidated state due to lack of investment. And would you be able to get greater insights into social benefits in these cases?
Yeah. Okay. Well, that's a really interesting one. Network Rail, as I was saying earlier, Network Rail is coming in to build a station in October. That station will be around for about 6 months, and so there might be some interest. I'm sure if you and we and Network Rail got together, we can probably think through ways of capitalizing on the fact that that's going to be there, and there may be some benefit on that. And I think the answer to the question is yes, there is. I'm sure. So give you a rough idea. That station will be about 100 meters long. Platform. It will include elements of booking hall, ticket hall facilities, some station platform buildings, so waiting rooms and things like that. They're looking to test their new hub design, which is one of the things that is being built in cross-laminated timber, try and reduce the carbon footprint. And also at the same time, this might interest you actually, is they are wanting to revise their lighting standards. And what they realize is that we can actually do that, because we can not only look at their lighting, we can bring their lights in if they want to, but we can make lighting standards, but also we can put the lighting behind it. So our lighting system could give you daylight or twilight or early morning or late evening, and what happens when the sun is shining in your eyes and all that sort of stuff. And so how easy is it to see the platform indicators, train indicators? How easy, a big problem for them is the driver at the front of the train who's sort of bathed in the light because it's all near the exit, for example, so quite high light level, trying to figure out, is there a passenger at the far end of the platform in a black coat, with a black hat, with a black muffler, and so on? Can they actually see them? And the Elizabeth line, they've got 24 screens to look at before they can figure out whether to shut the doors. And it's there's things in there that are really, I think, ripe for looking at, that we could do, because we can then reproduce that and tweak it. Well, what happens if it's lit like that? What happens if you do this? And I think one of the things that we've learned here is how important the hue of light is. So the color. So you tend to, most lighting standards tend to say something like it has to be 200 lux on the toe of the platform or something like that. It doesn't say what the hue should be. Sometimes they will say something about a color temperature because they've kind of read about it. But actually, these days, now, I mean, in the last probably 5 or less years, lighting technology has completely transformed. We have in here, the lighting system in here, we have each lighting unit has 10 lenses. Behind each lens is about 50 LEDs. Those LEDs are divided into 11 different wavelength bands. And we go from ultraviolet into infrared. And we can vary the if you like, the hue of the light by simply changing those intensities. It's exactly how your mobile phone works, except that the mobile phone has a red, green, and blue chip, and we have, in effect, 12. And those chips actually match what we call the gamut of the human eye, which is essentially the color sensitivity of the human eye. So your phone gets about 40 million colors by blending red, green, and blue. I have no idea how many colors we could actually do, so it doesn't really work like that. But if you were to film us scrolling through all of the colors that we can produce with your phone, you would have a massive amount of black and white and some color. But if you were looking at it, you would just see it completely just change color. That's because your eyes have a sensitivity that your phone simply doesn't have. And it's the same for the Hollywood cameras. They want to come and calibrate their cameras in our lighting system because of that. Now, I wouldn't say that that the railway industry has to go off and buy lights like mine I'm there so you can figure out what is the wavelength mix that you want on your railway for what purpose, because you can then specify that to the people who make the chips, because it's basically I went wavelength shopping basically, and we tested out different how to make those 11 bands, and we tested out different things and worked out what was useful, what was not useful. And basically, so if you go to an LED chip manufacturer and you say, I want blue chips, they'll get out a big bucket of chips and they'll say, here, this is blue. And in there will be, each chip will be slightly different, with a slightly different, it'll be vibrating to slightly different frequencies. So it'll be, a little bit more blue, less blue, that sort of thing. And if you just went and asked for a blue chip, they just give you a chip. I went in there and said, I want a blue chip between 380 nanometers and 405 nanometers. Give me a few thousand of them. And that's what we had. And then we did the same thing through the frequencies. Now, if what came out of research that you did in our lab was actually we get a much more comfortable lighting effect for passengers on the train or on the station or whatever, with a color temperature of this, with a blend of these frequencies, you could specify that to a manufacturer and they could give you that, and it wouldn't actually cost you any more than just simply buying a chip. The price is essentially is the same. They just, what the difference is how many they set aside that they don't give you. It doesn't alter the price because they're going to sell them to somebody else. So it doesn't matter. And I think what we can do is we can help to kind of focalize the idea about what kind of lighting is really helpful. And so I'll just give you an example, which I don't think would necessarily apply to the railway. It might. But about 20 years ago, a new photoreceptor was discovered. Well, it's not new. They just didn't know it was there in the eye. So you're familiar with the sort of red, green, blue, or long, medium, and short wavelength photoreceptors that we have, and we have 6 million of them in each eye. But they discovered another one. And why they'd missed it before is that this one is not connected to the vision system. So this photoreceptor, it receives light, it responds to light between 480 and 490 nanometers. And it's connected to a part of the brain that basically controls your biorhythms in your body. So what happens is, in the morning, the intensity of short wavelength light is greater than long wavelength light. So light feels a little bit bluer. And in the afternoon, the relative intensities change, so that the short wavelengths sort of die off a bit and the long wavelengths increase a bit. Now, what this photoreceptor does, it understands in the morning, it sees this short wavelength light, and it says, okay, there's lots of that, and it tells this part of the brain, and the brain then switches off the mechanism for releasing melatonin into the bloodstream. And in the afternoon, as that intensity subsides and the longer wavelengths come into play, it allows melatonin to be released. Now, what that does is it helps you go to sleep. So in the morning, it wakes you up, and in the afternoon, it helps you go to sleep. This is the underneath of all jet lag. So if you go to an old people's home, older people, they have an issue often with light, and grandmothers are often very famous for saying it's all dull and dim and things like that. And that's because the lenses are becoming cloudier through age, and therefore less light is getting into the eyes, so they're feeling they don't have enough light. So old people's homes, very often they ramp up the light levels in order for people to feel better. It's fine, except that light level includes this wavelength band. So by ramping up the light level, increasing the intensity of the light, including this band, they are actually stimulating the suppression of melatonin, and therefore they're not preparing for sleep. And what is one of the big problems for old people's homes is getting people to sleep. So they give them a sleeping tablet. And you sort of kind of think, it's one I'm really keen to do, is can we make a light source that essentially is a white light, which does not have that wavelength in it. You really wouldn't notice it. It's the most disgusting color you ever saw. You really wouldn't notice. It's a kind of very nasty cyan color. If we remove that, so we just make a light that does not have that wavelength in it, it would still be a white light. But it would not be stimulating the body to respond in a unfortunate way. Now, are there similar kinds of things that we can look at which relate to things like behavior in stations, behavior in trains, what kind of light should you have in the driver's cabin? All of these kinds of questions, which have been kind of really difficult in the past because the technology has not been there to be able to do anything. But now it's just a question of specification. And I suspect that the railway industry doesn't know enough about, and probably a lot of other people don't as well, doesn't know enough about what could be possible if they were to exercise that kind of knowledge. And certainly, that's the kind of thing that we could be helpful with, I think.
Absolutely, yeah, that's great. There's another question in the chat around that asked, were there any particular challenges around actually building the Pearl facility, or in fact when you set up for any specific tests?
Okay, so building the Pearl facility was a grand object. We actually built it during the COVID pandemics and lockdowns and things like that. And well, the biggest challenge was actually, and we were very lucky. We appointed some really good architects who distinguished themselves by listening, which is not necessarily the most common characteristic of architects. And they I needed to have a very, very big open space with no columns. So we have a 40-meter span building here. So what I'm sitting in here actually is I'm sitting in a window. I don't know whether you can see that. So that wall behind me there, that wall is about 1.2 meters deep. So we have like these deep reveals into the window. That is the size of the column that is holding the roof up. And I spent a long time trying to explain to structural engineers why I didn't want columns in the building, because we need the flexibility to be able to build whatever, wherever, and so on. So that was really important. So that was a bit of a challenge. Getting the heating ventilation sorted was another one, where they said I had to put partitions in it, otherwise it would be too expensive to heat. And then I took them to Pamela, the previous lab, and I took them up on the platform. So they went up 1 meter, and I said, how much warmer do you feel 1 meter up compared with the floor? And they said, well, it is warmer because we've just come up 1 meter. I said, yes. Now the new building is 14 meters tall. And I don't really care what happens to the temperature above, say, 2 or 3 meters. So what we have is a heating system where we take the hot air out to the top of the building, we run it through some heat source pumps, air source heat pumps, and take the heat out, mix it with fresh air if we need to for carbon dioxide and air quality, things like that, adjust the temperature and bring it in at the bottom of the building. And that is all done at a hyper slow speed, so you can't hear it. And that was a solution which they came up with, because we kind of challenged them, said, no, I can't have partitions, and I think we were really lucky. We had a design team who were able to have that kind of conversation with us as a client, and I think that was quite unusual. So I think those were kind of challenges, getting the big thing built and things like that. In terms of setups for experiments, my view is that people come to me and I sort of say, yes, I'm sure we can build this. My technicians go mad when I do it, man. But I say, yes, we can build that, but we just have to figure out how. The one that possibly one of the most difficult ones that we've been asked to do is to create the environment for the journey to Mars. So we can take all the light out of the building. That's easy. I've been in conversations with the astronomers about figuring out what you would see out of the window of a spacecraft going to Mars, and we think we can reproduce that. And we can get the the crew or whatever it is of the spacecraft, we can get them to sort of float. But if they had a pen in their hand and they drop the pen, I can't stop the pen from falling. So we're trying to figure out what the best way is of doing that. So that is my current. That's one of the toughest. How do I get rid of gravity? In other words, which is giving us a little bit of a challenge, but it's a nice one to have.
Wow, yeah, that is a challenge. Right. I haven't seen any more questions in the chat. I don't know if anyone else wants to put their hand up, ask a question.
Go on, I'll go again if you don't mind, Toby.
Yeah, go for it.
Sorry, Nick. It just occurred to me that this Scion type wavelength that you're talking about, which appears, I guess, in the afternoon, naturally in the morning, and that's the one that suppresses the melatonin.
That's it. Yeah.
So effectively, it disappears in the afternoon. Is that correct?
That's it. So the melatonin is then not suppressed in the afternoon, so it starts to flow.
So I can now explain to my father-in-law, who's a professor of chemistry, why he has to have a siesta in the afternoon.
Yes, yeah, absolutely.
Because he lives in Spain.
Oh, right, yeah. Well, of course they do, and that's partly also because of another interesting thing that we're also looking at, which you might want to be interested in the railway industry a bit more, is the value of the biome, so the microbiome. So having gardens, even if it's just grass, is actually a really, really good benefit. And one of the reasons for the siesta in Spain is because of the heat, the digestion of the midday meal gets very confused with having to deal with the heat in the afternoon. So the siesta kind of takes you out of the heat and allows the digestion to happen in a more natural way. In the northern hemisphere, you don't have that kind of tension so much, but in Spain it is. So it's to do with that. But actually, yeah, I mean, I've been trying to convince Transport for London to put grass on the top of all their bus stops, in order to distribute the microbiome much more effectively, because there is actually a socioeconomic gain to that. It means that people are less liable, less prone to infection from low-grade infections, so feeling, cold and gutty and all that sort of stuff, is because the microbiome's out of order, is too weak. So because we have too much sterilized food and all that stuff, and so a colleague of mine has been working on this, and he said, well, the reason is that the human being has co-evolved with bacteria. And bacteria, of course, are way older than human beings, and they're like billions of years old. And so because we co-evolved, we kind of work together. And what happens, I mean, if you take antibiotics, for example, it just kills all the biotics, and including the good ones, and the advert says, the good ones. And so I said to him, well, where can we get these things from? And he said, well, actually grass, because that's how we've evolved. And so if you just had a layer of grass on the top of a bus stop shelter, that would distribute that. So we have 20,000 bus stops in London. You can put it all around London. Now, the big interesting thing is they did an experiment where they checked out the quality of the gut microbiome in people who spent 2 weeks in the Lake District on the grass, and compared that with people who were walking down streets where there were front gardens with grass. And they found that the people walking down the streets with front gardens with grass, they ingested a much stronger microbiome than the people in the Lake District. And the reason is that there's a kind of rate of ingestion. So the lake, just simply bathing yourself in it, going and sitting in it for 2 weeks, doesn't do it, because you can't absorb it quickly enough. But the people who every day are just walking down to the newsagent or something, they are actually able to ingest that at the rate that the body can absorb it. And so that tends to favor people in lower socioeconomic groups and things like that if they have grass. And it only has to be grass. It doesn't have to be anything fancy. And so what we were thinking was that bus stops, because they're sort of kind of around, maybe that's a way in which we could actually improve the health. Now that then turns into them having fewer days off work, fewer days difficulty looking after the kids, all of those sorts of things that come which affect people in more challenging social groups that in a way, and this would just happen. I think it'd be really, really interesting to be able to get in there and measure that and see what's actually going on.
That sounds fascinating.
So you put it on the station. Yeah.
Thank you, Nick.
We can try that on Network Rail station when it's here.
That's brilliant. Thank you very much, Nick. Thanks for taking all those questions and answering them so thoroughly. And just wanted to take the opportunity to thank you once again for taking some time out of your day today and coming to present to us and really giving such an interesting presentation. And I've learned a lot tonight. And I really hope that we can get a site visit booked in for this year, and we come and see it for ourselves. That would be
please
great.
Yeah, come and play. Yeah, you never know what will be here. That's what the one thing I can't guarantee is what will be here when you come.
Well, I'm fine with that. I'm fine. But if you've got anti-gravity sorted by then, that would be perfect.
Yeah, working on it. Yeah.
Brilliant.
Okay. Your
space, well, thank you very much for the opportunity.
Sickness tablets, yeah.
Yes. Yeah, thank you very much for the opportunity. I hope it's been helpful.
Yeah, fantastic. Thank you.
Thank you, Nick.
Okay, cheers.